We're going to start dynamics by looking at some things that we looked at in grade 11 already, just we're going to apply our vector components' new model of thinking to those things. So first of all, we need to remember that weight, when we say the word weight, we're actually referring to the force of gravity. That's it. And if you remember, the force of gravity has a formula. It's mass times the acceleration of gravity wherever you are. Most of the time we're talking about being near the surface of the Earth, and so we'd say that g is 9.8 meters per second down. But we can apply that to all sorts of different places. So if you're on the moon, it's going to be different. If it's Jupiter, it's different as well. We're going to remember that the normal force is the support force applied by a surface. And maybe you'll remember that normal in math and science means 90 degrees. It means perpendicular. Okay, and so that's why it's called the normal force. Not because it's ordinary or regular, but because it's perpendicular to the surface. That's important. Tension is a force exerted through a rope. So when you pull on a rope or chain or cable, whatever, when you pull on something like that, it's going to pull back in the opposite direction. And that's called tension, or at least that's how we're... We should also remember that the units of force equals mass times acceleration, are kilograms for mass times meters per second squared. You can write it like this. There's a whole bunch of different ways of writing it. This is the same as kilogram meters per second squared. This is the same as kilogram meters seconds -2. So if we could just put -2 in the exponent, then that puts seconds on the bottom of the fraction and squares it. All of these things are the same. So we want to remember that those kilogram meters per second squared are the base unit of force. Now we name that something. We name that newtons, right? That's technically a named unit. It's not the base unit of force, and that's not really very important for your problem-solving purposes, but it might come up a little bit later. So the first thing about force that we're going to re-talk about, just like we did in grade 11, is forces in equilibrium. And equilibrium means balance. And hopefully you will remember that equilibrium happens when acceleration equals 0. Okay, and that happens when something is at rest, then the acceleration is 0, or when something is moving at a constant velocity. So keep your eye out for the words constant velocity or constant speed, and those will always tell you that all the forces are in equilibrium. So we are going to look at 3 different situations of forces in equilibrium, and we're going to apply our components of vectors problem-solving method to it. The first one we've called mild. Shouldn't be too bad. So we've got this giant physics crate suspended by 2 ropes. Who knows why? It's just the world that we build in physics, isn't it? So we know that this physics box has the force of gravity pulling down on it. We also know that it's suspended by 2 cables, and so the force of gravity is pulling against those 2 cables, and that produces a tension in the other direction. And it happens that we have 2 of those. Now there's no reason that I made these arrows shorter than the whole thing. It doesn't really matter. I just wanted to draw those so that you could see what direction the tension was. So we're going to call this one T1 and this one T2. Doesn't really matter which way you name them, so if you really wanted to make the left-hand one T1, feel free. So we know that because this thing is in equilibrium, that the acceleration is 0, and so if we would write down our full F net equals ma formula, we know that this a here is going to be 0 meters per second squared, and when we split F net into all the forces that are acting on this box, we've got tension 1 plus tension 2 and I'm going to say minus Fg. So I've put in the direction of the force of gravity right away, and that means that the rest of the problem, when I'm solving it, I'm just working in magnitudes and not directions anymore. Okay, so that's an option that you always have. So I've called up positive and down negative. That's arbitrary. You could flip it the other way if you wanted to. But all of these things together equal 0 newtons, because our mass, 20 kilograms, times 0 meters per second squared, is 0 newtons. And so if I add this force of gravity to the other side, I end up with T1 plus T2, my two upward forces, are equal to the force of gravity, my downward force. Now again, I already put the direction in for the force of gravity, and so what this says is that the magnitude of the two tensions are equal to the magnitude of the force of gravity, or the magnitude of the two tensions is equal to the magnitude of the force of gravity. So now I can solve for these two tensions. Now I can only do that because I know that these tensions must be the same. Okay, there's no angle difference, there's no length difference, nothing is different about those two ropes, and so they must be the same amount of tension. Okay, so I'm going to put this up here, T1 equals T2. That's important for this one. Now, all of these things should have arrows on them, at least at the beginning, but again, I've filled in the directions, and so technically we're working in magnitudes now and not so much with vectors anymore. Okay, so T1 plus T2 is the force of gravity, but because T1 and T2 are equal, then this is the same thing as saying 2 times T1 equals the force of gravity. Okay, now if you wanted to, you could have started the question, you started your problem solving right there. You didn't necessarily need to do this F net equals 0 and then split it into its pieces. Because it's an equilibrium situation, we know that the downward forces must equal the upward forces. Okay, and so you are welcome to start right here. Yeah, maybe you should start right there and not right over here. We'll get rid of this. Maybe you should start on there. And then this next step, you should show why that's true. Okay, and so I did that up here where I said T1 equals T2. So now, because I have the formula for the force of gravity, mass times 9.8 in this case, then I can solve for T1. And that's why this one is mild, because there are no hoops to jump through here. The only leap that you have to make is knowing that T1 equals T2. And so we end up with T1 is equal to 20 kilograms times 9.8 meters per second squared divided by 2. And that gives me 98 newtons upward. And that is equal to T1, and it's also equal to T2. Now I put the direction on there as well, so these are now vectors that I'm working with. Okay, so 98 newtons upward is T1 and T2, each of them. And that's why they balance out this 196 newtons, this 20 times 9.8, that's 196 newtons. So our total downward force is 196, so our total upward force must also be 196 in order to balance that out, in order to have equilibrium. And so then those 98 Newton tensions will balance that out. Alright, let's try the medium one. A large scoreboard is suspended from the ceiling of an arena by 10 strong cables. Weird way to mount a scoreboard, but sure. 6 of the cables make an angle of 8 degrees with the vertical, while the other 4 make an angle of 10 degrees. If the tension in each cable is 1,300 newtons, what is the scoreboard's mass? So what this is saying is that we've got a scoreboard like this, and it's got 6 cables making an 8-degree angle with the vertical. So let's say, I'm going to exaggerate this for the sake of the drawing. There you go. And then 4 of them make an angle of 10 degrees. I'm also going to exaggerate that. Okay, and so here is our vertical, and here's our vertical. And so what this is saying is that this is 8 degrees, and this is 10 degrees. Now really there are 6 cables here, so there are 6 of those, and there are 4 cables here, so 4 of those. Okay, but we can really kind of consider it to be one cable and then divide it by 6 in the end, and consider the other one to be one cable and then divide it by 4. So that doesn't really make the question more complicated necessarily. Just think of it like you have tension 1, which is that way, and tension 2, which is that way, and then we're going to divide them afterwards. Okay, so we want to figure out what the tension, or sorry, what the scoreboard's mass is given the tension in those cables. So each cable has a 1300 Newton force acting on it. So let's just look at this first one here as though it is a single cable. So we're going to call this T1. T1 is 1300 newtons. And there's 6 of those, remember? We're going to split this into components. Now we're going to split this into components because what we're looking for is the scoreboard's mass, and the only place that we can get that mass from is the force of gravity, right? Because that's mass times 9.8. And so if we can figure out what the force of gravity is, then we can figure out what the mass is. So we need to know what the force of gravity acting on that scoreboard is. And we're going to get that from the Y tensions in the cables, right? Because the scoreboard is not moving, that means that F net equals ma, F net equals 0, right? Because the acceleration is 0. And so then the situation that we find here is that T1y plus T2y equals the force of gravity. Okay, so these are our upward forces. This is our downward force. And because there's no vertical acceleration, or horizontal acceleration for that matter, that means that those two things must be balanced. Okay, now in this case, T1y and T2y are not going to be the same thing. So we can't just do it that simple way. We have to calculate T1y and we have to calculate T2y separately. So this is the thing that we're looking for, T1y, that component right there. And if we figure that out, knowing that this angle is 8 degrees, we want to use cosine for that, right? Because this is the adjacent side, T1y is the adjacent side, and T1, which we're given, 1300 newtons, is the hypotenuse. So adjacent and hypotenuse goes with cosine, and if you'd set that up and rearrange it, what you'd end up with is T1y is equal to the hypotenuse, 1300 newtons, times the cosine of 8 degrees. Now be a little bit careful with just assuming that it's always the number that you're given times the cosine of the angle or times the sine of the angle, because that won't always be the case. It will always be the case if the number you're given is the hypotenuse, this one, and you are splitting it into components. Then it will always look like this. Okay, and you just kind of get used to that. And so I kind of skipped to that part. So this is equal to 1,287.3 newtons. Okay, and we need to remember that that is in each cable, because the 1300 newtons is in each cable, not just in the total of whatever 6 cables that was. So then when we're going to look for T2y, it's the same idea. You've got T2 pulling this way, and you can split it into its x and y components like this. And the angle that we're given is 10 degrees right there. And so it ends up being the same thing, cosine as well, and each cable also has 1300 newtons of force in it, cosine 10 degrees. And so that's 1,280.3 newtons in each cable. Okay, so that's the part of the question that's different than the mild one. You have to split your tensions into components and then use the correct components to figure out the piece of information you're looking for. And at this point we can go over to this fact that we wrote down at the beginning, that these two tensions put together equal the force of gravity. So let's do that. Let's just write this down one more time. T1y plus T2y is equal to the force of gravity. Okay, and we're looking at just magnitudes here. So I don't need to put in negatives anywhere at this point, because what I've done is I have already put in the directions at the very beginning. The very beginning would have been F net equals 0, and then T1y plus T2y minus the force of gravity equals 0, and then you move the force of gravity to the other side. Okay, so I've already put in the directions at the beginning, so I do not need to call the force of gravity negative here. I already did that at the beginning. So I know that T1y, well, it's actually 6 of them, right? So we should really go like this. 6 T1y's and 4 T2y's equal the force of gravity. That is true. Don't forget that there were 6 of one cable and 4 of the other. But again, that doesn't make much difference to us because we're just doing 6. It makes a difference to the answer if you forget it or not, but it doesn't make a big difference to the problem-solving process in this type of question. So 6 times 1287.3 newtons plus 4 times 1280.3 newtons equals mass times 9.8 meters per second squared. And so when you put all this together, you get 7,723.8. That's the total tension in all of those T1 cables, plus 5121.2. That's the tension in all of the T2 cables. And we want to divide that by 9.8 meters per second squared. And that gives us the mass. And so now our mass is equal to 1,310 kilograms.